Okay, welcome to the second presentation in the Advances in Research and Innovation stream at the SNOMED CT Expo 2023. For those you haven't heard already, my name is Rory Davidson. I'm the Chief Information Officer at SNOMED International, and I'll be moderating today's session. All questions will be answered at the conclusion of the presentation. Online attendees, please use the Q&A button within the Zoom Events app to type your questions to the presenter, and I will pass them on. On-site attendees, please use the microphone provided by the camera there. I'm now very pleased to introduce Anthony Shek from the Guy's and St Thomas Hospital, who will be presenting Foresight-generative pre-trained transformer GPT for modeling of patient timelines using electronic patient records. Over to you, Anthony.
Fantastic. Well, thanks, Rory, and thank you, SNOMED, for having me here today presenting. Just before I begin, I'd like to say a huge thank you to all the funders and the team that we have as part of the university and all the hospitals and all the doctors that have been involved with this project. So before I even get on to the tool that I'm going to build, I'm just going to give you a bit of a, the way I'm going to do or run this presentation is give you a bit of a background of the latest or roughly how a transformer model works and what is a generative AI. I'll talk about, well, how does it relate, or why are we talking about this in the context of SNOMED CT, and how do I then build sort of these timelines and build a tool from using these latest tools. And then, of course, evaluating the tools that I built, or this tool called Foresight. But without spoiling anything, first of all, let's start off with large language models. So this all belongs to a field called natural language processing. And this is just a field that is basically to help understand or how computers process and understand free text and natural language, because I guess computers can't read, they understand things in binary or in code. And so I guess the first step for an LLM is to translate it into words or into a language that they themselves understand. So in this case, if I said, taking this example, they had a seizure in the morning, the computer, what does that mean? How do I understand this? And so the first step is to break it down into bite-sized chunks. And this is called, in the individual unit, it's called a token. And so it's a unit of text that can be on a character, word, paragraph level, sentence. And so it manages into bite-sized pieces. And so this process is called tokenization, and the component of these large language models or models to do it is called a tokenizer. So these large language models are called large because they use enormous amounts of data sets, or the size of the data set is huge, to get millions of examples, and they scale based on their parameters and the amount of data that it's being exposed to. And so to understand the meaning of a word, in this case, seizure, using our example, you take a huge data set like the entirety of Wikipedia or the internet in some cases. And so from that, running through multiple examples, the model is exposed to the word or this mention of seizure in many different contexts. And so what it does is take notes of how it's used in which context. And so what we end up with, or these models end up with, is a huge corpus or an array of words that appear close to this target word, and also words that are distant and are not relevant. And this is all based around the assumption that similar words are used in similar contexts. So in this example that I put up, if I said that the word fit and seizure, there can be synonyms of each other. They can be closely related in meaning, yet at the same time, they're different words. They can be used, especially fit, in different contexts as well. So using this example, the patient collapsed because they had a seizure, I can interchange the word fit into that as well, meaning that there is some sort of relation there. So although seizure relates to epilepsy, there are certain scenarios, like the bottom one, a diagnosis of epilepsy does not seizure. It doesn't make any sense. And so when we go through these many different examples of which words appear close to other words and which words appear distant or further, which tokens, the way how we represent this is in a computer way of understanding, and that's through a mathematical representation or a vector. And this is also known as a vector representation of this token, or a word or an embedding. And this is how computers can read and understand language. And so as you iterate through the many different examples, the words that appear closer help change the meaning, and you can change this vector representation. And words that appear further away will change the vector representation in a different way. And so what do I mean by different or similar? So these vector representations are basically coordinates. If we consider this vector, if we have an example of a vector representation that was of 2 dimensions, you can call them X and Y coordinates. Or if it's 3 dimensions, X, Y, and Z, and you can map them out and you can visualize it. So if it's a 2-dimensional vector, and you can position them because they're coordinates, if they're more similar in meaning, they will appear closer together. Whereas words that's further apart, it would move them apart. So in this case, of course, large language models use more than 1 or 2 or 3 dimensions. They often use 300 and more dimensions to capture the meaning of the word. And so these word embeddings consist of hundreds of values, with each of these values representing a distinct meaning or representation of what the word means. So to choose a vector representation, you can either certainly make it larger, so that can capture more of the contextual information in that representation. However, it costs more compute. So that's why there's a trade-off, and that's why you end up having these standards of 300, 768, or 1024 for the large language models. And that tends to be the correct balance of how to represent your individual tokens or units. And so you can't just say, okay, in this dimension, this specific part, this means that this is a procedure or a disorder, because the way how it is originally initialized is set at random. And actually, it's all relative to each other. And so ideally, these pairs of words that I've shown here, similar meanings, they should have similar embeddings or be in this similar position in this high dimensional space. So if we look at MRI and dialysis here, the first 4 positions, they tend to be high in value, and that probably, you can say, it represents a procedure or something like that. We can't know for sure, but it's all about relative, the relative distribution according to each other. So we know that there is some sort of similarity between the two. But that's not the only clever thing about how these models work. And the key thing of what's really accelerated this drive in AI is something called the transformer architecture, which I'm not going to go into too much detail about, but a key component of this is what we call attention. And this attention mechanism is what allows these language models to understand relationships between words. So previously, we used to weight words based on when we sequentially process them. We used to weight each word before and how it influences the next word. So these old models, like a couple years old, that's not that old, they could also have the capability of generating new text, but they didn't perform very well. And this is simply because the words before or directly before had heavier weights to it to predict the next word. And that's not necessarily the case, or why of how we should be using language to predict the next word or sequence of tokens. And so what the attention mechanism does or allows you to do is, first of all, compute all the different words to understand the relationships. And this allows you to take advantage of these hardware architectures like GPU, where it allows you to do parallel processing. And so this was mentioned in this paper called Attention is All You Need by fellows and people working at Google. And essentially what it does is it looks at each token in a body of text and decides which words or other tokens are important to understand its meaning. And the attention mechanism allows you to calculate and figure out which weight in the context is important to derive the meaning. So in this case, I had epileptic has a higher weight to influence what the meaning in this fit of the word fit means in this context. Whereas if we switch out the context a little bit, the attention to different words in the context changes in their weight as well, where software and system influences and changes the meaning of fit here. So that's essentially what attention mechanism does in short. It just allows you to focus on the specific parts of the sentence or sequence that is important to derive the meaning. And this is what changes the embedding or the representation and allows you to capture the contextual relationships inside of it. And so in summary of this basic of this mechanism of how these language models work, you have a sequence of tokens, you represent them, you encode them, and now you have a machine understandable representation of natural language. So how does this relate to SNOMED CT? Sorry, before that, what can you do with it now? You have a computer that can understand and represent text in a more natural way of how akin to what humans do. And so other than translation, a key thing is natural language generation. That's the really hot topic at the moment of this field of generative AI. And so in this case, you can do a next word or next sequence token prediction, similar to, I guess we've all used ChatGPT, and this is how it works. Essentially tries to predict the next token or sequence of tokens based on probabilities. And so, yeah, now moving on to it, how does this relate to SNOMED CT? And so what have we done? So taking that background of how these models work and how we can use them and use the attention mechanism to forecast which is the next token in the sequence to be predicted, we introduce, or I'm proud to introduce, Foresight. And this essentially uses the existing knowledge from patient records, of real world patient records, and represents each patient's medical history as a sequence of SNOMED CT concepts, where you can take and linearize in a longitudinal manner a patient's history as a sequence of SNOMED CT concepts, and that allows you to forecast what will happen next to the patient and predict what's the next SNOMED CT concept to appear in the patient timeline. So exactly the same as ChatGPT trying to predict the next series of words, we're trying to predict the next disease, disorder, SNOMED CT concept. So first of all, the majority of natural language, the natural important clinical language that's present in patient records is in unstructured format. So we first need to extract and standardize the free language. And so in this case, in this example, we have a demonstration of a tool called MedCat, where we can standardize free text and extract SNOMED CT concepts from the free text and also contextualize them, whether it's negations, hypothetical, or does it belong to the patient. And so now that we've pulled some structure from this unstructured text, we can then create a longitudinal data set of the patient and represent this patient through their series of documents of when the medical record was written in a trajectory or in a linear timeline. Taking account of demographics and age of when these occur, you essentially are creating a sentence or a sequence now of SNOMED CT concepts. And so just a bit of background about the data sets that we're working with. So there's two main hospital sites that we work with in London. And that was, other than Guy's St Thomas, one is King's College Hospital, which is a large general, one of the largest hospitals in the UK. One is South London and Maudsley, which is a specialist mental health hospital. And we tried it out with Mimics 3, an open source data set as well. And so we're talking about tens of millions of documents here. And so there's a bit of SNOMED that we did prepare and we edited. And so we only looked at various semantic tags that was relevant to the patient. So the subsection of SNOMED that was relevant for us was the disorders, findings, medications, procedures, and substances. And so that's about 200,000 concepts. And so when you can label and linearize and create these patient trajectories of what's happened to patients that have already gone through the hospital system, you can then use that as your training data set in equivalent of ChatGPT reading through the internet and understanding sentences and languages and paragraphs and stories and books. Our model goes through the hospital record and understands what happened to the patient. Diabetes, diabetic, they didn't take their medication, developed complications, diabetic retinopathy, diabetic foot. This works because medicine has patterns. And so once you train it and you can visualize each patient as a sequence of concepts, you can then input and play around with it and input a timeline of a new patient trajectory and then ask it to forecast. You can not only just forecast, you taking advantage of the structure of SNOMED CT based on SNOMED tag, you can ask the filter which drug is likely to be given next, which medication and which disease is which diagnosis or which symptoms are they to expect. So that's the part of the forecasting. So you can filter and change it around. And if you're familiar with SNOMED, have a bit of fun. And so this is what the platform looks. It's very much a research platform at the moment. You can click and play around and look at the parent-child relationships, add it. You can test out the different models and biases that are present in these models because they're very different data sets. You can also ask it to predict, well, what is the exact next SNOMED CT concept that should be mentioned or that is mentioned in this next document, or is it, or you maybe what's the disorder, what's the medication, etc. So you can build a timeline, you can predict, and then it will give you the prediction for rank. You can also ask it to show its saliency or explainability about which parts of the sequence has the model paid attention to arrive at its answer as well. So there's some example timelines. You can click it, play around, and you can also, if you're not familiar with SNOMED CT, you can just enter a bit of free text and play around with it that way. And so here are some example synthetic timelines that we've generated from each of these trusts, where we just enter the demographics of a patient. And in this case, a 43-year-old ethnically Black female. And so we just asked the model, well, what's going to happen next? And so there are, because of the patterns that, or the data sets it's been exposed to, there's lots of biases that's been attended. And so it's learned and captured this all from the data set, which can be a good point in some ways because it's more representative, but it's also something to keep in mind and bad because it may not generalize well to other data sets depending on your use case. So for example, in KCH, a large general hospital, it's predicting hypertension, neck pain. Patient is a non-smoker in this case. Whereas the mental health model, it focuses a lot more and it's captured a lot more of the mental health aspects. And just assume that if you go to this hospital, you're probably having something with your mental health. There's also a Mimic-3 example, which helps describe a little bit of the Mimic-3 data set. And so, well, how does it perform? It's okay. And so when you're trying to predict what the exact next SNOMED CT concept is, it's about 60% accurate. So that may not sound like a lot, but it's really, really powerful. If you're trying to say which one out of these 200,000 concepts is likely to come next in this trajectory, you know, if you're kind of halfway right, it's choosing the next exact one is actually quite a top performer. But when the performance increases, when you say, okay, maybe don't choose the next one, could it be one of the next 5 or one of the next 10? And then you just increase the performance significantly, where even the top, just give me 10 suggestions of the next disease, and it tends to be quite right. So, and this is not, I guess, not really surprising because diseases and disorders and medications have patterns. You take a diabetic medication if you have diabetes, you take hypertension, antihypertensive medications if you have high blood pressure. And so what can you do with this tool, you know, or tools like this in the future? So this is just a demonstration of what is one of the possibilities here. And so of course you can, for clinical risk prediction, you know, has the doctor explained everything to the patient of what could or may not happen, or have they considered this or that? And so you can, if you forecast, you can really have a look and consider this. Of course, what everyone tries to do is can you predict which diagnosis based on the symptoms that the patient presents with? You know, can you essentially learn from all the patients that have used the hospital system and apply it to new patients coming in? I guess this kind of makes sense. Models are very good at pattern recognition. Doctors call this experience. You can also forecast costs. And cost forecasting is possible because SNOMED has a nice mapping to ICD-10. And so you have a trajectory, and as you predict which series of codes are present, you can map it to which ICD-10 code and how much this patient's going to cost and things like that. But an exciting one that I'm particularly excited about is this digital twin and virtual trial emulation. That's a new part of which I think is one of the key applications in research. And so a digital twin is simply a digital representation of the patient. And that's what we've done here. You know, a patient timeline, a patient health trajectory is represented as a sequence of SNOMED CT concepts. And so this allows you to then digitally intervene with this health trajectory. What happens if they take drug A versus drug B, and then predict what would occur later on? Of course, it's not perfectly accurate, but it gives some sort of idea from patients that have used the system. So it's a bit more of this idea of, can you learn from a very messy data set where people are of different ages, genders, ethnicities, and comorbidities as well, and can a large language model untangle all those patterns to give you a bit more of an accurate picture, or a more accurate representation of a real world scenario? So in this case, in this example, we're comparing levetiracetam to lamotrigine. These are just completely made up, but it just gives you an example of, okay, with this drug A, this is the projected timeline, drug B, this is the predicted timeline of the interactions, stuff like that. And so there are various limitations, of course, with every tool and every new tool that comes out with. And so right now, it can only predict concepts that are seen in the training data set. And so if this was done before COVID, it would never predict or be able to predict COVID, the concept of the coronavirus. It may be able to get close to something related to influenza, chest infection, pulmonary embolism, things like that, but it would never be able to predict the concept that doesn't exist. It cannot accurately estimate when the concept will happen or when the disease will happen, which would be very interesting, but I'm sure there's techniques to be able to fine tune that, but we haven't done that at the moment because we've just sort of mismatched it together roughly. And lastly, it learns that biases in the data. One thing, I guess, yes, of course, the advantage of this is pattern recognition, but it can also learn bad things and bad habits. I mean, not necessarily bad, but the thing is, clinical practice evolves and changes over time. And so the recommendations applying to new may not follow the latest guidelines or treatments for this patients. So that's one thing, another thing to keep aware of. And so there's probably, I mean, there will be alternative routes to apply and make suggestions based on new clinical guidelines. That's all future work. So on that note, thank you very much for listening. I hope this was something that was useful and maybe a little bit inspiring. But there's all the source code is hosted by my team on Cogstack. And so there's a variety of tools to explore, some using SNOMED, CT. And yeah, if you've got any questions, please let me know. Thank you.
Thank you very much. Anthony will take some questions now. As a reminder in the room, please take the microphone as you're up, Kinwa.
Kinwa Fung from National Library of Medicine. So Anthony, thank you very much for sharing with us this exciting work. So I have two questions basically. So the first one is related to what we talked about yesterday, the role of terminology in all this learning. So you have, I think, presumed that the normalization of free text into a standard terminology will kind of improve the performance. But I wonder whether you have thought about doing actually some like a parallel exercise training just on the free text and see whether there's any deterioration in the performance or not. And my second question relates to the timeline. So your evaluation is based on the accuracy of predicting a certain diagnosis or drug, but what kind of timeline are you talking about? And have you analyzed the time between the prediction and what it happens? I mean, how it affects your accuracy of prediction? Thank you.
Thank you. So answer the first question. So of course, if you improve the way of extracting concepts into the model and to linearize it, it will certainly improve the performance. But another key point to add to that of what we're, of course, when you sort of reduce free text to SNOMED CT concept, you lose the contextual information. And I know SNOMED's concept sometimes try to add severe stroke, or I mean, let's use example headache, severe headache, painful headache, nail biting headache. And so actually this contextual information can influence a prediction quite a lot. And so I think Foresight 2.0 will take into consideration that part of free text around it. And so the reason why we use SNOMED CT and not just the whole of the free text is that SNOMED CT helps to clean up a lot of the unnecessary garbage in the free text and just all the redundant bit of information. It helps to standardize all the variety of nomenclature. So fits, episode, seizure, they can all mean the same thing depending on context. So that's why we use SNOMED CT to standardize all the acronyms, synonyms, ambiguous terms, and things like that. And so, yeah, so that's why we use SNOMED CT, but you can kind of do a hybrid approach of what you're suggesting, use the SNOMED CT and then look at the contextual information that influences it, which may suggest. The second question was about the timeline of that prediction. And so we essentially, the only bit of timeline that we add is actually the age for now. And when they grow up another year, because that's quite something that we can add quite clearly. Its timeline is a bit messy, simply because you can only predict what is mentioned in a record, right? So just because the patient has come in 6 months or 9 months later with a diagnosis of, and then they get diagnosed of diabetes, it technically doesn't mean that it didn't happen. Like this disease occurred a month before. And so evaluating when it didn't happen isn't quite appropriate. Yeah. So maybe there are different ways of being able to do it. I think it'll be absolutely fantastic if we can figure out when and where a certain disease happens. I mean, not where, so when a disease happens or when a diagnosis is about to happen or the symptoms of what to expect. But yeah, that's quite a bit of a challenging approach. So that's why there's not really any metrics on that.
I've got a question online from Mohammed Nofal Nordin. Hello, I'm quite interested in your project where you're utilizing a GPT model for your NLP task in SNOMED CT. I'm curious to know if you've explored the use of other open source transformer models like Llama 2 or Mistral for training or fine tuning in the specific NLP task. Could you please share your insights on how the performance of GPT compares to these models in the context of entity extraction with SNOMED CT?
Yeah, so these, so everything that you mentioned are GPT-based models. And so they're just fine-tuned, trained on different data sets and maybe have slightly a different mechanism where it's an attention window or context and it's slight, but fundamentally they're all GPT or generative pre-trained transformer models. And so you would certainly use those kind of models rather than your BERT architectures or when you have the encoder decoder models, because those types of models look at past and future to be able to understand the context of this concept. Whereas GPT, there is no future because that's something they're trying to generate. So definitely, as you said, Mistral or Llama 2 architectures are appropriate. Over here, we did use, this was based on GPT-3. And so sure, the performance will change slightly, but it's very much customized for this use case. And maybe there's certain things that we can learn from the architectures of these models or latest models that have come out. Maybe there's something to learn, but it's yet to be explored.
Great, thank you very much. And with that, we'll conclude the session. Thank you very much, Anthony. Online delegates can join other sessions through the event lobby. So thank you.
Thank you.